Imagine a particle, not a grain of sand, but something among the smallest bits of existence that matter can break into. This particle doesn't behave like a tiny billiard ball. Left alone in the dark, in the space between events, it doesn't have a location. It exists in a blur of every possible location simultaneously. It is dancing everywhere and nowhere at once. This isn't a metaphor. It is the calculated, measured, undeniable behavior of the reality beneath our own. But here is the mystery that fractures our world. This ghostly dance stops the moment anything observes it. Light hits it, a sensor measures it, a conscious mind turns to look, and the blur solidifies. The particle becomes a single point. So what is the world when we aren't looking? What exists in that space between observations? And if the universe behaves so differently when no one is watching, is there something that always is? In a quiet house in Princeton, one man could not close his eyes. Eugene Wigner had helped build the edifice of quantum mechanics, but he could not ignore what the foundation was made of. He was a giant. He discovered the deep symmetries that govern the rules of nature, work that earned him a Nobel Prize. His colleagues admired his clarity, but this clarity became a curse. At night, he could not stop thinking about the observer. Wigner imagined a friend in a sealed laboratory, measuring a particle. To anyone outside that room, the friend and the particle remained in a blur of possibilities until the door opened. But inside, the friend experienced a definite outcome instantly. So which reality is real? For Wigner, the chain of observers could not be infinite. It must stop at a conscious mind, a mind that stands outside the quantum system and collapses it by simply being aware. This led him somewhere he did not expect. If consciousness forces reality to choose, then what is consciousness? He could not answer with physics alone. He began writing about philosophy, about a universal mind, even about God. For him, it was not a leap of faith. It was the only logical conclusion if quantum mechanics tells the whole story. This search cost him. He called the quantum paradox a profound irritation. He argued with colleagues in the corridors of Princeton, filled notebooks with attempts to reconcile the blur with the solid world, and lay awake long after the lamps were out. The question had become personal. It had become real. Wigner never found his answer, but he showed that the question lives not just in a lab, but in the mind of anyone willing to look into the dark and wonder what is looking back. A thin sheet of metal in a dark room, two narrow slits cut side by side, a gun that fires electrons one at a time, a screen that glows wherever an electron lands. The setup is absurdly simple. The result is not. You expect two bright lines. That is what particles do. They go through one hole or the other and pile up behind. But as the dots accumulate on the screen, a different pattern emerges, a ladder of alternating bright and dark stripes. An interference pattern. This is what waves do. But you fired electrons, individual, bullet-like particles. How can a single electron know where all the others landed to build that pattern? It cannot. Each electron must be going through both slits simultaneously, as a wave, interfering with itself. So what happens when you try to catch it in the act? You place a detector at one slit to see which path the electron chooses. The interference vanishes. The pattern collapses into two lines. The electron, the moment it is measured, becomes a particle again. This is not a trick. It has been repeated thousands of times, with photons, with atoms, even with large molecules. The result is always the same. The behavior changes when something watches. When physicists first confronted this, they were shaken. They argued, redesigned the experiment, silenced the detectors, but the behavior held. The universe at its smallest scale does not play by classical rules. And this forces a question that cannot be dismissed. What exactly is an observation? Is it the measuring device, the data, or is it the conscious mind that becomes aware of the result? If observation requires awareness, then a century of experiments suggest that consciousness is not a passive byproduct of physics. It may be woven into the fabric of reality. This is the experiment that broke the classical world open, and it is the question that kept Eugene Wigner staring at the ceiling long after the lights went out. A telescope in the Chilean desert. It is pointed at nothing, an empty patch of sky that holds no star, no galaxy, but the telescope is patient. It is waiting for a ghost, the faintest microwave glow, older than anything. Light that left its source before the first atom formed. That source was the universe itself, smaller than a single atom, expanding at unimaginable speed, and at that size, it was a quantum system. Every particle that would become you was there, smeared out as a wave of probability, not yet decided. The double-slit experiment is not a laboratory oddity. It is the universe's original rulebook. The carbon in your bones was fused inside stars only because quantum tunneling allowed atomic nuclei to overcome their repulsion. The green of a leaf exists because electrons jump between energy levels. Your own solidity is a quantum effect. The Pauli exclusion principle prevents atoms from passing through each other. These rules are not optional. 8 billion years. The earliest cosmos was a quantum foam, where tiny spontaneous fluctuations were stretched into the seeds of every galaxy we see. The stars ignited because of quantum chance. The sky above you is a frozen quantum event. Now consider, if an observation is required to freeze possibilities into reality, then what observed the early universe? Before there were eyes or instruments or even atoms, what collapsed the cosmic wave function? Did the universe hang as a blur of maybes for billions of years, waiting for something to become aware of it? That is the question Wigner glimpsed, and it escalates. Either consciousness has always been present in some form, or quantum mechanics does not apply at all scales, or existence itself is weirder than we ever imagined. We do not know which is true. The search for that answer may be the deepest journey science has ever started. A black and white photograph from 1927. 29 men in suits and bow ties, arranged in rows before a hotel in Brussels. Some of them look weary, as if the arguments have just ended. In the center, a man with a rumpled jacket and wild white hair stares at the camera with a kind of defiance. That man is Albert Einstein. To his right sits Niels Bohr, pipe in hand, looking like a patient professor. They were friends. But that week they nearly tore physics apart. The issue was simple. Does reality exist independently of us? Einstein believed it must. For him, the idea that a particle had no definite position until measured was an insult to reason. He said God does not play dice, but he did not mean it as a religious statement. He meant that the universe must be governed by rules we can know, not by chance. Bohr took the opposite view. Quantum mechanics was not incomplete. It was the final word. The universe at its core is probabilistic, and he warned anyone who would listen, if quantum mechanics hasn't profoundly shocked you, you haven't understood it. The debates became legendary. Einstein would arrive each morning with a new thought experiment, a clever trap designed to show that quantum mechanics leads to contradictions. Bohr would listen, pace the room, then return the next day with a refutation. This went on for years. The struggle was not just intellectual. Friendships fractured. The old order of classical physics, the certainty that had driven Newton and Maxwell, was crumbling. Einstein, the man who had dethroned Newton, found himself defending the very determinism he had once helped to undermine. The debates never truly ended. In a sense, they continue today. Every physicist who works on quantum foundations is, knowingly or not, taking sides in that argument. And the question Bohr and Einstein could not settle remains. Is reality made of things or of possibilities? We still do not have an answer, but the photograph endures, a frozen moment from a time when two men wrestled with the fabric of existence itself, and neither could win. In a laboratory, a crystal splits a single photon into two. They fly apart in opposite directions, but they remain connected across any distance. Measure one, and the other instantly takes the corresponding state. This is quantum entanglement, and since the 1970s, experiments have proven it is real. In 1964, the Irish physicist John Bell was working at CERN, surrounded by the largest machines ever built, but his weapon was paper and pen. He became obsessed with this mystery. He suspected each particle might carry hidden instructions that predetermined its behavior. He derived a simple theorem that could test this idea. If hidden instructions exist, the results of certain measurements would fall below a specific limit. If quantum randomness is fundamental, they would exceed it. experimentalists took up the challenge. First John Clauser in 1972, then Elaine Aspect in 1982, then Anton Zeilinger in the 1990s. Each experiment pushed the limits further. The results systematically exceeded the limit. Hidden instructions do not exist. The connection is instantaneous, and it is real. Einstein's spooky action at a distance is not a mistake. It is how the universe works. To grasp the implications, consider scale. The Milky Way spans 100,000 light-years. Two entangled photons at opposite edges would respond to each other as if no time passed. Light takes 100,000 years to cross that gap. The quantum connection ignores it entirely. Space, the stage we assume to be fundamental, becomes irrelevant. This challenges our deepest assumption. That objects are separate, that you end here and I begin there. At the quantum level, separation is not a given. The universe is a web of relationships, not a collection of isolated things. Individuality may be a coarse-grained illusion. John Bell died in 1990, still troubled by what he had discovered. He wrote, "I cannot accept a universe that is fundamentally non-local, but the experiments leave no room for doubt. We still do not understand why this is true. The question remains open. What does it mean for a universe to be connected at its deepest level? We are only beginning to ask." A sealed steel box sits on a laboratory bench. Inside, a cat, a flask of poison, and a single atom waiting to decay. According to the equations, before anyone looks inside, the cat is neither dead nor alive but both. This is not a metaphor. It is the literal prediction of quantum mechanics, and it forces a question. Where does the list of possibilities become a single reality? Erwin Schrödinger invented this experiment in 1935, hoping to show quantum mechanics must be wrong. But the problem did not go away. It grew, and three different answers emerged, each reshaping how we understand existence. The Copenhagen interpretation says that measurement itself forces reality to choose. Before measurement, the cat is in a blur of both states. After, it is definite, but this places a heavy burden on the word measurement. If measurement requires a conscious observer, then reality needs a mind to become solid. A position that begins to sound like the universe requires a watcher. The many worlds interpretation takes a different path. Proposed by Hugh Everett as a graduate student, it says the cat never collapses. Instead, both outcomes occur, each in its own parallel world. In one reality, the cat lives. In another, it dies. And the wave of branching continues for every quantum event, producing an infinite tree of universes. If this is correct, then you exist in countless versions, each believing they are the only one. The third option, objective collapse, rejects both observer dependence and infinite branching. It says the wave function collapses spontaneously, triggered by a physical threshold like gravity. The collapse is random, fundamental, and independent of any mind. Reality is self-determining, but it is also inherently chancy. These are not just technical alternatives. They are visions of what reality is. If Copenhagen and consciousness are linked, then mind is as fundamental as matter. If many worlds is true, then every possibility is actualized, and the universe is infinitely larger and stranger than we thought. If objective collapse, then randomness is the bedrock, and there is no hidden script. More than 70 years after Schrödinger's cat, we still have no way to decide between these interpretations. The experiments are not conclusive. The question remains open, and perhaps that is the deepest lesson. Quantum mechanics does not give us an answer to what reality is. It forces us to ask the question more clearly and to live with the uncertainty it brings. Fred Hoyle was not a man searching for God. He was an astrophysicist at Cambridge, trying to solve how stars forge carbon, the element of life. His calculations predicted a specific energy level, a resonance in the carbon nucleus. Without it, carbon would be rare, and life would have no basis. When experiments confirmed the resonance exactly where he predicted, Hoyle was shaken. He later said the fine-tuning made him feel that a superintellect had monkeyed with physics. He remained an atheist, but the precision of that number stayed with him. That precision extends across all of physics. Gravity is just strong enough to hold galaxies together, but weak enough not to crush stars. The cosmological constant is measured to 1 part in 10 to the 120th power. If it were any larger, the universe would have blown apart before stars formed. If it were smaller, matter would have collapsed. The dials are set with a delicacy that seems impossible. The Copenhagen interpretation gives these coincidences a philosophical weight. If a conscious observer must collapse the wave function for reality to become definite, then mind is not an accident. It is a participant, even a requirement. This is the strong anthropic principle. The universe must produce observers. Some see this as evidence that a cosmic consciousness underlies the whole system. Mind is fundamental, and perhaps that mind is what we call God. But counterarguments stand firm. The weak anthropic principle says we can only observe a universe that allows observers. Seeing a tuned universe is no surprise, because we could not see the untuned ones. Many worlds dissolves the mystery entirely. If all possible universes exist, tuned ones are inevitable, and we happen to be in one. Objective collapse says the constants are brute facts. No explanation is required. Each interpretation points in a different direction. Copenhagen toward a cosmic mind, many worlds toward a multiverse where design is unnecessary. Objective collapse toward blind chance. No experiment has decided between them. The question of whether a mind lies behind the universe is not answered by quantum mechanics. It is only sharpened by it. The data does not resolve the mystery. It forces us to live with the question, and that may be the deepest truth we can reach. A boundary that never stops moving. Every time we take a step forward, it retreats by the same measure. This is the frontier of understanding, and quantum mechanics is the place where we feel it most sharply. John Bell spent his career trying to pin down what the theory actually says about reality. He proved that the universe cannot be both local and real. But the deeper question, what is real, he left unanswered. On his desk at the time of his death in 1990, the problem's still open. We do not know what measurement is. We call it the measurement problem, but that label hides the truth. There is no mechanism, no story that explains how a blur of possibilities becomes a single definite world. We only know that it does. We do not know why the universe follows these particular laws instead of any other. The constants feel tuned, but that feeling is not evidence. It is a question without an answer, and perhaps a question without a solution. We do not know if consciousness is fundamental or an outcome of complexity. If it is fundamental, then mind was present from the first instant. If it emerges, then we are late arrivals in a universe that did not require us. Both possibilities remain open. Each of these unknowns is a door. We stand in front of them without a key. That is not a failure of science. It is the honest condition of being human at this moment in history. The question does not go away. It becomes our horizon. All we can do is hold it carefully and keep walking toward it. If you have your own sense of where this frontier lies, share it in the comments. We are all walking the same boundary, and no one has crossed it yet. We return to the space between, where a particle both is and is not, where possibility hangs before it falls into one reality. This gap is larger than any answer physics will ever give us. We do not know if quantum mechanics points toward God. We do not know if mind is cause or effect, but the mystery itself is not a flaw. It is the ground we walk on. Carry it with you. Let it change how you see the ordinary, and if you stand in that space between, leave a comment. The question belongs to all of us.